Let's see. So thanks very much for having me here. It's good to be back at Google. And I appreciate whenever people come out for a talk on this completely crazy title, The Big Picture on the Origins of Life, Meaning the Universe Itself. Usually the response I get when people first see the title is, who do you think you are? How presumptuous must you be to think that you can talk about these things? So I want to get the disclaimer right on the board right away, which is that I do not know what the origin of life is. I do not know what the origin of the universe is, and I do not know the meaning of life. What I do think is that we have a way of talking about these things now that is sort of better than we had before. If before, I mean 500 years ago. And so this is not so much a set of answers to difficult questions as it is encouragement to continue the conversation within a particular framework. And I'd like to start by telling the story of Lucia de Burke. She was a Dutch nurse. In 2004, she was convicted to a sentence of life imprisonment for murdering several infants under her care. Now, this is a sad story, but if you look into it, there was an interesting thing about the legal proceedings, which is that there essentially wasn't any evidence she had done it. And you might ask, how is it possible that someone gets convicted of basically being a mass murderer without any direct evidence? There were no eyewitnesses that saw her do anything, no poison in her handbag or anything like that. And the answer is mathematics. The prosecution asked statisticians to estimate the likelihood that this number of children would die when a certain nurse was on duty, and they said, oh, it's 1 in a million chance or 1 in hundreds of millions of chance. That was the primary reason why she was convicted. Now later, other mathematicians looked at it and realized that it had been bad mathematics. The argument was it was more like a 1 in 25 or 1 in 100 chance that something like that would happen, which, as I'm sure you all know, those chances happen all the time. In fact, someone pointed out that the total death rate for children in this hospital, I mean, it's a pediatric care hospital, there's 6 children there, the death rate went down after she was hired, which is not the effect you would expect the hiring of a serial killer to really have. But the other question is, besides the bad mathematics, why were the people on the jury so easily swayed, even though there was no direct evidence that she had actually done it? And I like to point to the possibility that really it was part of our very human desire to blame something when something happens. Rather than to think that just things happen and that there's a little bit of irrationality and randomness in the world, we like to think there is a reason why things happen. So when a whole bunch of children die more than we might expect, we want someone to blame. And once that starts, we convince ourselves that we are on the right track, finding this reason for this happening. The picture on the left is what Lucia de Burke actually looks like. The picture on the right is the courtroom sketch of what she looks like. Once you decide that this person is the evil one who is responsible for this, then you look at her in a slightly different way. Fortunately, the bad math went away, the good math took over, and she was released, she was exonerated, and found innocent later on. But the idea that we find reasons why things happen is not necessarily a bad one. It's an ancient one, and it goes back to some of the greatest thinkers in history. Aristotle very famously had what he called the 4 causes for things happening, which we might really think of as 4 kinds of explanation why things occur. And one of them was the final cause for something. The final cause for Aristotle is the reason for which something exists, the goal for which it is created in the first place. The final cause of a seed is to grow into a tree, for example. And this kind of reasoning, this kind of metaphysical view that the world at its deepest levels is a story of causes and effects, went through to these guys. This is Spinoza and Leibniz, Baruch Spinoza and Gottfried Leibniz. And they promulgated something we call the principle of sufficient reason. They also promulgated a principle that philosophers' hair gets better and better over time, as you see. I think that Leibniz got artificial help, but overall, there's certainly a progress in nature that we can observe here. The principle of sufficient reason is simply the statement that everything happens for a reason. You can find this on bumper stickers and greeting cards, but Leibniz in particular raised it to the level of a metaphysical principle. For everything that happens, there is a cause or reason why. And again, it's not crazy. In our everyday experience, that is kind of what we see. Things do not just happen. The book is not going to just fly off into air. There seems to be reasons why things happen. If the book moves, it's because I moved it. And for Aristotle and for many other people, this metaphysical claim that things that happen do so because something causes them to happen influence their ideas about physics. So for Aristotle, if things are moving, it implies that something is moving them. There is a reason why things are moving. And his reasoning is quite straightforward. If I start pushing on the book, it will move. And if I stop, it stops. There you go. That's the basis for a way of thinking about physics. That if you see things moving in the world, you need to explain that. You need to find the reason why, what the mover is. And this extends from individual objects like books to everything in the universe. The universe is full of motions. But to Aristotle, the natural state of being was for things to stay stationary. So the existence of all these motions and transformations of all sorts implies that there is something behind the scenes causing those kinds of motions. That is not how we think about fundamental physics today. Over the course of improved explanation and experimentation and theorizing, we have a very, very different way of thinking about how the world works at its most fundamental level. But it's not a way that we make a big deal out of. You know, there's many things that popularizations of science will talk about over and over again, right? You can't go faster than the speed of light. You can't know your position and velocity at the same time. But we don't talk about the fact that the whole principle of cause and effect as a fundamental organizing principle for the universe is no longer part of our best theories of physics. Some people talked about it. Bertrand Russell liked to emphasize it. He was primarily a philosopher, but a mathematical philosopher who knew a lot of physics. And he said, "The law of causality, I believe, like much that passes muster among philosophers, is a relic of a bygone age. Surviving, like the monarchy," he just had to get that in there. He couldn't stick to just the philosophy and science, "only because it is erroneously supposed to do no harm." So this should be, I hoped, in your minds, quite an extraordinary claim. The law of causality, that you have a cause for every effect, that the cause precedes the effect, that's not part of our understanding of the world anymore? What is going on? Well, it's not that anything can happen. It's not that because there's no cause and effect at the deep level, the book can in fact just fly all over the place. The point is that we have replaced the principle that causes precede effects with the principle that the world is governed by patterns. And this happened slowly. Here is one example, sort of the tipping point, if you will, from one way of thinking about the world to another one, was the principle we call conservation of momentum. If any of you in the room have taken physics classes, you have been tortured by the principle of conservation of momentum to sort of find the solution when different balls bump into each other and so forth. But in fact, this principle is at the heart of a whole new way of thinking about how reality works at a deep level. It took hundreds of years and many, many smart people to think of it. One of the primary people was Ibn Sina, who was a Persian polymath. To a modern physicist like me, Ibn Sina is extremely annoying because he wasn't even a physicist, primarily. He was a doctor. He was a medical doctor. He wrote a lot about the human body and anatomy. He did physics in his spare time, and he invented conservation of momentum. This is very annoying to me. But he wouldn't have said conservation of momentum. Again, it took hundreds of years to get it right. The basic idea that Ibn Sina put his finger on is that if you could remove friction, if you could remove dissipation, if you imagine something moving through the vacuum, it would keep moving forever. This was the invention of that other device that physics teachers like to use to torture people, the frictionless surface. If you imagine something moving in the complete absence of friction, it would not slow down and require a cause to keep moving. It would just keep moving. And this principle was improved upon by people like Galileo, who did experiments, and finally Christian Huygens was the one who actually formulated our modern mathematical notion of conservation of momentum. So why is conservation of momentum such a big deal over and above the fact that it's a tool for physicists to use? Because it implies that there's a different way that the world naturally is. If you're Aristotle, the natural way for things to be is to kind of sit there in their happy place, and you need to do something to get them moving. In a world with conservation of momentum, the natural thing for the world is to move and change. And it implies you don't need to explain why things are moving. Things just naturally move. And this was developed over time and probably reached the pinnacle with Pierre-Simon Laplace, a French mathematician and physicist around the year 1800. He did not invent classical mechanics. It was Newton, as we all know, who really put the finishing touches on classical mechanics. But you can make the argument that Laplace was the first person to really internalize what it meant, the deep implications of this Newtonian clockwork universe worldview. So you know that if you do a physics problem, and again, you ignore friction and dissipation and so forth, you play physics billiards, physicists billiards, where balls can just bump into each other and so forth, you can solve the problem of these two balls are moving with certain velocities, they scatter and they go off in another direction. What is the direction and the speed at which the balls are going to go? Laplace was the first to point out that that process is reversible. That if you started up here saying now the balls are moving apart, what were they doing in the past? And Newton's laws make an absolutely clear prediction for what they were doing in this world where you can ignore friction and dissipation. If you made a movie of this whole process and played it backward, it would look completely plausible. So Laplace invented what we now call Laplace's demon, or what he called a vast intellect. Laplace's demon is something that has the ability, what we would now really call it is a really good computer. Maybe you have a Laplace's demon in one of the other buildings. If Laplace's demon knew everything about the state of the universe at one moment in time, the position and the momentum of every particle moving in the universe, then Laplace says that vast intellect would know the future and past just as surely as the present. If that vast intellect knew all the laws of physics and was able to calculate what would happen, there would be nothing that would be uncertain to that intellect about what would happen in the future, what had happened in the past. So this is, even though it's a subtle difference, a crucially different way of thinking about the world. It's not that this configuration of stuff causes this one and therefore causes that. All of them are related by a pattern called the laws of physics. Just like the integers, 0, 1, 2, 3, minus 1, minus 2, minus 3, the number 2 happens after the number 1 and before the number 3. But we don't say that the number 1 is the cause of number 2, or 2 is the cause of 3. We just say that every number is 1 bigger or less than the numbers next to it. It's just a pattern that follows, and you can go forward or backward equally well. And Laplace says that is what the world is like at a deep level. Now these days we know better than Newtonian mechanics, right? We've had quantum mechanics, we have statistical mechanics, general relativity, and so forth. But the basic Laplacian principle remains the same. It's just the actual laws that we have are different. So one of the claims I make in the book that I would like to defend is that this audacious sounding idea that the laws of physics underlying everyday life are completely known. Now when I say this, people like to stop listening when I say underlying everyday life, so I want to emphasize that. I'm not saying the laws of physics are completely known. I'm not also saying that everyday life is completely known. There's plenty of things about everyday life that I don't know about. Plenty of things about physics we don't know about. Dark matter, dark energy, black holes, the Big Bang. Plenty of physics that is not about the underlying laws that we don't know. High temperature superconductivity, turbulence, and so forth. I'm making quite a specific claim that you and I, and all the stuff right in front of us, literally the stuff we can touch and see in our everyday lives, these are made of things, atoms, electrons, protons, neutrons. Those protons and neutrons are made of quarks. And all these particles interact in a certain way, and we know both what those particles are and how they interact. When I say we know, not only do we have a good idea, but 1,000 years from now or 1,000,000 years from now, this idea will still be right. Hopefully we will learn more. I mean, maybe the quarks and electrons and so forth are made of even tinier things. That's great. But there won't stop being quarks and electrons, and we won't be wrong about how they interact. And there are deep reasons for believing this is true. Let me just tell you what the ingredients are. This is an atom, right? This is a neutron and a proton and an electron, so it's a deuterium isotope of hydrogen. The electron is held together to the nucleus by electromagnetism. The individual protons and neutrons are made of quarks, up and down quarks, which are held together with a strong nuclear force. Occasionally, an up quark or a down quark can convert into the other one via the weak nuclear force and give off a neutrino in the process. Everything is pulled toward everything else by gravity, and everything swims in the background of the Higgs field. The Higgs boson particle is something we discovered just in 2012 with the Large Hadron Collider. The particle is what happens when you start this field vibrating. But the field itself, the Higgs field, pervades all of space, affects the properties of the other particles that we're made of. There are more particles than this. These matter particles, the electron, the quarks, and neutrinos, they all have heavier cousins, but they decay away very, very quickly if you try to make them. They do not affect our everyday lives. We know them and we can complete them into theory, but you don't actually need to know them to know what you and I are made out of. So that's it as far as our everyday world is concerned. The point is that there is no new particle, no new field, no new force that we will ever discover that will have an impact on our literal everyday biology or environment like what holds this table up. We hope to discover a lot more physics. It will not affect you or what you're made out of. So I know that this is I keep being told this is a technically inclined audience, so you don't like the picture. The picture makes you nervous. You want an equation, so here it is. This is what Nobel laureate Frank Wilczek has called the core theory. And he invented the name to emphasize that we usually distinguish between the standard model of particle physics and general relativity, our best theory of gravity. And the reason we do that is because general relativity is a classical theory, not a quantum theory. We don't have a full and complete theory of quantum gravity yet. What gets lost in that true statement is that we have a pretty good everyday theory of quantum gravity. We know quantum gravity in the regime where fields are weak. We know quantum gravity perfectly well if you want to use it to calculate the moon orbiting around the Earth, for example. So if you're literally only interested in the regime of everyday life, this is it, including gravity. This is basically the Feynman path integral, the probability to go from one amplitude in a field theory to another one. And I'm not going to go through all the details, but basically you see how all of the different pieces of modern physics get involved. There's quantum mechanics, space-time, gravity. This is Einstein's general relativity right there. All the other forces, electromagnetism and the nuclear forces, the matter particles of which we are made, and the Higgs in the background. If you want to know more about the details, I did manage to squeeze it into the book, but I was told it should be put into an appendix, and the font size is very small in the appendix. But nevertheless, every term here is explained briefly. It takes a year-long quantum field theory course in graduate school to get the details, but I at least say what every term means, including the I, for example, and including the K less than lambda. What you don't see are causes, purposes, or reasons why. It's just Laplacian calculation over and over again. This is the modern version of what you need to program into Laplace's daemon so that starting from the position and configuration of the world at one point, it can find out what will happen next or what happened before. The final criterion you need for this to be a good, successful theory is that it should fit on a t-shirt. So we did the experiment. There it is. Totally fits on the t-shirt. You can buy them at my website. I don't make any money off them, but you can buy the t-shirts. All right. So I want to do at least 1 minute of justification for this grandiose claim. I mean, it's one thing to have a theory. We have lots of theories. Our theories are never complete. Our theories are never things we should have 100% credence in. We should always, as scientists, be willing to improve upon our theories. So what gives me the right to say that a million years from now, this is still going to be the theory underlying the particles and forces of which you and I are made? The answer is something called crossing symmetry, which is a feature of quantum field theory. I mentioned fields. Fields are, in fact, what you and I are made out of. You might have taken a physics course and been asked, is light a particle or a wave, or is an electron a particle or a wave? Probably you were not told the answer. It's a wave. That's what it is. According to quantum mechanics, the world is made of waves. The world looks like particles when we look closely enough. But really, the way that we talk about the world in modern physics is through quantum field theory. And quantum field theory uses these little pictures called Feynman diagrams. My personal claim to fame in the world of physics is that the desk I have in my office at Caltech used to be owned by Richard Feynman. So I sit at Feynman's old desk. I leave blank pieces of paper in there hoping some diagrams will appear, but it never happens. So what Feynman did is to invent a way of talking about what happens in particle physics, in quantum field theory, and also how likely it is to happen. So if we have a particle we know about, like a proton, and we imagine there's a new particle. Maybe there's a new particle that really does affect how you chew your food or how plants photosynthesize or how you think. Well, then there must be a Feynman diagram that says that that particle can interact with a proton via some new interaction. And Feynman's rules say how you can use this diagram to calculate how likely that is to happen, the amplitude or the probability of that process. And then crossing symmetry says, this is a diagram that time evolves from left to right, so x comes in, p comes in, they just scatter off of each other. Crossing symmetry says that if this diagram exists, I can rotate it clockwise by 90 degrees and get another diagram that exists. So I'm glossing over the difference between particles and antiparticles here. Really, if this is a proton and this is still a proton, this diagram talks about a proton and an antiproton coming together to produce an X particle and an anti-X particle. And what crossing symmetry says is that if you know how big this diagram is, if you know how likely that process is, you know how likely this process is. So if this new X particle interacts with protons or with neutrons or quarks or neutrinos or whatever, strongly enough to affect your everyday life, then we could make it by smashing together the particles out of which we are created. And the punchline is, we have looked. We've smashed together all the particles. We've smashed together protons and protons. That's what the LHC is doing. We've done protons and antiprotons, electrons and electrons, electrons and positrons, on down the line. We would have loved to find a new particle like this, and we have not done so yet. There are no particles like this. The closest we have, there's a tiny little bit of a hint at the Large Hadron Collider as of May 2016, that there might be a new particle that is 800 times the mass of the proton. It may or may not be true. There's a little bump. Maybe it's there. We're still looking. But even if it is, it decays away in less than a zeptosecond. It is not something that affects your everyday life in any way. So in terms of the particles that actually matter to you and me, that make us up, we know the complete collection. So the question is, the big question ahead of us today is, if that's true, why does the manifest world of our everyday experience seem so different than the underlying laws of quantum mechanics and quantum field theory and particle physics? And the answer is this tricky idea called emergence. You can have an underlying layer of microscopic fundamental physics made of particles, forces, and differential equations. It can do what Laplace said: information is conserved from moment to moment over time. The rules of physics are patterns written down in differential equations. And yet, when you collect together many of these particles, there can be collective behavior that is implicit but not at all obvious in this microscopic rules. This collective behavior could emerge into wholly new concepts and vocabularies. So the idea that there are tables and chairs and peoples and planets, that's nowhere obvious in this underlying description. But the two levels can be compatible with each other. This is the world of cause and effect, reasons why, dissipation, and most importantly, the arrow of time, the difference between past and future. So our task today is to see how this one level can be compatible with the other one. Why can we think that there are reasons why and causes and effects, and for that matter, right and wrong and truth and beauty in the world, even though at some level, deep down, it's just stuff happening according to that equation that I showed you. So the arrow of time, one of my favorite topics, is simply the fact that the past and future are different from each other. This is not a surprising fact if you're Aristotle. Motion through time, the evolution of the universe, is obviously something profound. The past is different from the future because the past already happened. But according to Laplace, or to modern physics, there's no difference between moving toward the past and moving toward the future at the microscopic level. Only macroscopically is there a difference, and there are many differences. You can remember the past, but you can't remember the future. We were all younger in the past and will be older in the future. Sorry to break that to you. Most importantly, or most fundamentally, entropy increases over time. Entropy is the way that we have of talking about the disorderliness, the randomness, the disorganization of stuff over time. And there's a general principle that organized things like unbroken eggs can easily evolve into disorganized things like broken eggs, but never backward the other way, or at least very, very rarely, or at least you need to do a lot of work to make it happen. If you live in a room or you have an office and it's clean, it will naturally happen that it becomes messy over time. If your office or room is messy, it will never clean itself up all by itself. You need to do work. That's because entropy is increasing. If you like to think of it as the working out of a great law of physics, be my guest. And the reason why this is true is because there are more ways to be high entropy than to be low entropy. There are more arrangements of stuff that are messy than are organized. This was the brilliant insight of Ludwig Boltzmann, the 19th century physicist. And so therefore, if you start in a configuration of low entropy, entropy naturally increases. The problem was, therefore, why isn't entropy at its maximum value? There are many, many more ways for entropy to be high than for entropy to be low. Why is it true that entropy was ever low? So Boltzmann, in other words, explains why, given the entropy of the universe today, it will be higher tomorrow. There are more ways to be high entropy than to be low entropy. But he does not explain why it was lower yesterday. I'm here to tell you the answer. The reason the entropy of the universe was lower yesterday than today is because it was even lower the day before yesterday. And I know the reason why that's true too, because it was even lower the day before that. And this reasoning goes back 13.7 billion years to the Big Bang. The reason why the universe has had a low entropy all along is because it started that way. Nobody knows why. This is a profound question for modern cosmology. But once you give me that, I can explain all of the differences between the past and the future. So one way of thinking about it is, we all agree that there's no arrow of space, right? If you're out there in a spacesuit, there'd be no difference between up and down, left, right, forward, backward. But here in this room there is. If I drop the laser pointer, I know it's going to go down. There's an arrow of space pointing down. Nobody thinks that this is some profound consequence of the fundamental laws of physics. It's because we live in the vicinity of a very influential object, namely the Earth. The point of this discussion is that time is like that. There is no intrinsic arrow of time in the laws of physics, but we think that there is in our observable universe because we live in the aftermath of a very influential event, the Big Bang. I'm not going to explain why the Big Bang was low entropy, because nobody knows. Don't believe anyone who comes in here and tells you they know. It's a good topic for conversation. But given that, we can try to explain other features of the arrow of time. For instance, the existence of memories and causes, right? Memories are something where we know something now, it implies something about the past. A cause is something that we do something now, it implies something will happen in the future. Where does this asymmetry come from? So here's a memory. Here's a picture of a record of an event. This is an egg that was broken. You're walking down the street, you see a broken egg on the sidewalk. Ask yourself, what does the future hold for this egg? I don't know why you're asking yourself this. You're in a reflective mood. What is the future of this poor egg going to hold? You don't know. I mean, there's many different possibilities, right? It could just sit there for a long time. It could wash away in a rainstorm. Someone could clean it up. But if you ask yourself, what does the past of the egg probably experience? What were things like for the egg recently? With overwhelming probability, that egg used to be unbroken, and someone dropped it. Why is it that this single record, this isn't even moving, right? The macroscopic information is not changing in time. The egg is just sitting there stationary. Why are you able to draw such different conclusions about its past than its future? The answer is because secretly you know that the Big Bang had a low entropy. You don't use that in your everyday life, but that's why. If all you knew was physics and the macroscopic information about the egg, the number of things that could happen in the future would be exactly equal to the number of things that happened in the past. But the extra thing you know is that the universe started with low entropy. That ties the possible histories in the past, and what that means is that you know something about the past condition of the egg. Unbroken eggs lead to broken eggs because that's the easiest way to get to broken eggs given the low entropy past of the universe. And causes and effects work the same way. Just like an egg is something, a memory is something that if it were a little bit different now would imply something different about the past. Think about what a cause does. If I say, I move my hand and the book moves, if I move my hand a little bit differently, like I missed the book, then it wouldn't have moved, right? So if my hand moving is the cause of the book moving, that's because if my hand had done something very different, it would have implied something different about what comes next. If I'm waving my hand over here, I could wave in a slightly different way, and it doesn't imply anything different about the book, and therefore this hand moving is not the cause of the book. It's the thing that came right next to it that is the cause of the book moving. The idea that causes precede effects emerges in our macroscopic world because of the arrow of time. So that is the first little baby step towards reconciling our everyday world with this impersonal, calculational underlying laws of physics. The next step is, if the universe is just a story of stuff becoming more and more disorderly and entropic over time, Why are we here? Why is anything complex and intricate and organized exist in the universe? This is another good question to which we don't know the complete answer. But it's interesting that there's a big part of the answer, which is that simplicity versus complexity is a whole different axis on which to think about the world than low entropy versus high entropy. If you think about the classic example of entropy increasing, mixing cream together with coffee. You know that in this picture, this picture, this picture, time moves from left to right. It's easy to mix things. It's hard to unmix them. This is low entropy. That's high entropy. But this low entropy configuration with the cream on top, coffee on the bottom, is also very simple. Cream's on the top, coffee's on the bottom. Towards computer thinking people, it's algorithmically compressible. A small file size is necessary to tell you what happens macroscopically in that picture. But the same thing is true over here. It's high entropy, it's all mixed up, but it's still simple. It's all mixed up, that's all you need to know. The file size is also small here. It's in the middle where the cream and coffee are beginning to get mixed together, where the tendrils of cream and coffee are reaching into each other and a fractal pattern develops. That's where it's complex. This file size, to show you that picture, is bigger than the one on the left, the one on the right. So while entropy in the universe just increases monotonically, complexity first increases and then goes away. When entropy is very, very small, it's impossible to be complex because there's not that many possible arrangements you can be in. But when entropy is very, very large, it's impossible to be complex because everything is smooth and homogeneous. It's only in between the complexity is possible, and therefore it's not only compatible with the increase of entropy to see complex forms arise in the universe. It's because entropy is increasing that it could possibly happen. And this behavior of complexity going up and going down is not just cream and coffee. The universe is the same way. The universe started very simple and low entropy. Hot, dense, expanding universe near the Big Bang. It will end very simple and high entropy. Eventually all the stars will burn out, all the black holes will evaporate, and you'll have nothing but empty space. It will once again be very, very simple but high entropy. The last black hole will evaporate 10 to the 100 years from now. Yes, that's right. 1 Google years from now. Before you guys stole the word from us, this was a Google. Okay? The entropy of the universe increases monotonically through its history, but the complexity comes and goes. The universe became more and more complex up to the present day, and will start becoming less and less complex as those stars stop shining. The stars stopped shining about 1 quadrillion years after the Big Bang. So it's today, when gravity has pulled things together, made the universe lumpy, brought into existence planets and stars and galaxies, biospheres and people, that the universe is interesting and complex. As small as we are compared to the vastness of the cosmos, we live in the interesting part of the history of the universe for exactly that reason. And this kind of reasoning can help us explain even questions like why life itself exists. So I like to tell the story. I was once on a plane flight, going to a conference to give a talk. And as often happens, if you're a physicist or cosmologist, people find that out and they want to tell you their theories. Everyone, it seems, has a theory about the universe. I was reading some papers about statistical mechanics and the origin of life. The guy sitting next to me on the airplane says, "Oh yes, I've read those papers." So I'm a little bit skeptical. But he says, "In fact, I can tell you the purpose of life." And I'm very skeptical. But he says, "The purpose of life is to hydrogenate carbon dioxide." This was not the response I was expecting to get. It turns out that I was seated next to Dr. Michael Russell, one of the world's experts in abiogenesis, the origin of life. He works at JPL, just down the street from Caltech. And he writes papers with graphs like this, and he was very serious about the hydrogenation business. What he means, and again, we don't know whether this is true or not. We don't know how life began. This is one of the theories people are advancing, but you can see in all of these theories, you can sort of see the hints of how a really, really difficult problem suddenly seems to be a lot more soluble. So what Russell is pointing out that there are many environments in the early Earth where there's a lot of carbon dioxide and a lot of hydrogen, and that is a low entropy configuration. It has what we call a high free energy. So this is free energy versus different compound structures. If you took that carbon, removed the oxygen, and piled them all up with a bunch of hydrogen atoms, the carbon would now be in methane and the entropy would be much higher. In some sense, the carbon dioxide wants to become methane. The problem is that there's a barrier, that all the ways to get from CO2 to CH4 involve going through even lower entropy configurations, higher free energy configurations. And that can't happen all by itself. It's not like lighting a match on a candle. But what Russell points out is that it can happen if there's a complicated network of chemical reactions brought together in just the right way with the right catalysts and so forth. And that kind of network in the right conditions could be the precursor of the metabolism of modern life. So in the 1980s, on the basis of this kind of reasoning, Russell predicted the existence of a certain kind of underwater geological formation, what we call warm alkaline hydrothermal vents. And after he made the prediction, they found one. This is the Lost City configuration. Lost City, I don't know what it is. It's a bunch of stuff happening under the mid-Atlantic Ocean. And it has exactly the properties that you would need to get this kind of reaction starting. There might be many of them underneath the ocean. This is something that we think will probably last there for tens of thousands of years before it washes away and you make new ones. So we don't know how life began, but this way of thinking about it is interesting because rather than looking at it as life exists, how did it possibly start? This point of view is saying we have a puzzle, how to increase the entropy of the early Earth, and life is the solution to that puzzle. Of course, you need to get it together with other things like cell walls and replication and RNA and so forth. Putting all those pieces of the puzzle together is full employment for abiogenesis researchers for the next 100 years, probably. But then once that gets started, once you have life, then things get interesting. What is life, anyway? Nobody knows that either. I like the definition given by the physicist Erwin Schrödinger. Schrödinger said that life is something that keeps moving long after it should have stopped. What does he mean by that? He means if you put a dead thing in a bowl of water, it will just sit there, it won't do anything. If you put a living thing, like a goldfish, in my experience, it will also just die and then it will float to the bottom of the tank. But if you give it food, the living thing can last for a long time. What is food? Food is energy in a low entropy form. That's exactly what we get from the sun. The sun gives us energy, and you might think that's what's important. The sun gives us energy. But if the whole sky were the temperature of the sun, none of us would be here talking about it. We would come to thermal equilibrium. What the sun gives us is low entropy energy. For every one photon of light we get from the sun, we give back 20 photons back to the universe. But we get visible light and we radiate infrared. We radiate photons with 1/20th of the energy each. So we give back the same energy we get, but only after increasing its entropy by a factor of 20. By photosynthesizing, chewing our cud, having meetings, writing software, etc., then we radiate back into the universe having increased its disorder by a considerable fraction. And that's an individual, that explains how an individual organism can persist and survive and sustain itself. But of course, the great thing about life is that it reproduces and there are mutations. And therefore, evolution gets off the ground. So if our goal is to understand how ideas like cause and effect and even purposes can arise, evolution is a wonderful mechanism for making that happen. Why do giraffes have long necks? Well, one answer is because of the state of the universe and the laws of physics. But that's not a very helpful answer, is it? Another answer is to reach these leaves up there in the tree. Evolution can be thought of as a search strategy for this different genetic information, for the genome that passes down to try to maximize the chances of reproductive success in its particular environment. And given that strategy, it's perfectly okay to say the reason why the giraffe has a long neck is to reach those leaves. You can also see something like this in simple computer examples. This is a cellular automaton invented by computer scientist Melanie Mitchell. She calls it Robbie the Robot. Robbie had a party last night. There are beer cans scattered all over his house. What's the best algorithm to pick up the beer cans? Many of you are probably familiar with genetic algorithms. You just pick some random strategies, let them evolve, that is to say, find out which ones are most successful, cull them, randomly mutate them, find out which ones of those are most successful, and repeat this. And in very few generations, Robbie finds a better strategy than his human designers ever found. And once it has that strategy, are you allowed to say Robbie is, quote unquote, trying its best to pick up the cans? Sure, that's what I'm trying to say. There's no such thing as a real, true purpose that goes above and beyond a way of talking about what happens in the physical world. Evolution and the laws of physics and the arrow of time make it perfectly sensible that such ways of talking would become convenient and useful as complicated organisms adapt and go on. And that even counts for thinking, for consciousness itself. We, again, do not know how consciousness arose either. We don't even know what consciousness is or how it works. But we can see little steps that might have happened along the way. So Malcolm McIver, who's an engineer at Northwestern, likes to talk about the first fish to flap up onto land. The evolutionary pressures on land are very, very different than those under the water. If you're under the water, you can't see very far. The attenuation length of photons is a few meters. So you're swimming around at a few meters per second. You need to be able to instantly react to what you see. But then you climb up onto land, and now you can see for kilometers. So there's a whole new evolutionary pressure, which is to make a smart decision. You have the time to think about what to do. And what that means is that developing the capacity to contemplate different hypothetical futures becomes a smart thing to do. And we can look back, we can do the neuroscience and look in your brain, what are you doing when you're contemplating hypothetical futures, when you're really sort of consciously imagining different things? It's not a whole new module of your brain. You're using the same part of your brain that gets used when you recall a memory. This is exactly what evolution likes to do, to repurpose old parts of the functional organism to do new tasks. Imagining the future is one part of being consciousness. It's one part of being conscious. It's not the whole thing, obviously. But again, you could see how it would happen. We don't need to invoke anything beyond the particles and fields of the core theory to explain our consciousness. Here is a picture of my head. It's not to scale, but this was a map made in the laboratory of David Popple at NYU. It's evidence that I actually have a brain inside my skull, which I was happy to see. When you have a thought, in your neurons, there are literally charged particles jumping from one neuron to another. Any physicist will tell you, following the core theory, that charged particles in motion create magnetic fields. So this is an MEG, a magnetoencephalograph. It is literally an image of the tiny magnetic fields that stick outside of my skull while I was hearing some sounds, and my neurons are going, aha, yes, you are hearing some sounds. Now, this isn't evidence of anything very strong. It's just a reminder of the obvious fact that your thoughts and your dreams and your aspirations and your emotions are correlated with physical goings-on inside your brain. We don't need to go beyond that to explain what it is that is happening when you are thinking. This is, again, an ancient argument. It goes back to these folks. This is René Descartes, famous physicist, famous mathematician also. And this is Princess Elizabeth of Bohemia, considerably less famous, but they became friends and they carried on a long conversation. Basically because Descartes was always looking for a potential patron. And even an exiled royal family, like Princess Elizabeth's was, is better than no royal family at all. Unfortunately, she did not become his patron, and she did give him a hard time about his ideas. One of Descartes' favorite ideas was mind-body dualism. He thought that the mind or the soul was something immaterial and separate from the body. And Elizabeth pressed him on how in the world could something immaterial and without any location possibly influence the physical reality of our bodies? So he had a theory. This is the pineal gland in your brain. It's the one part of your brain that is not broken into two different hemispheres. So Descartes drew this picture and literally proposed that the soul communicated through your pineal gland with your body. Nobody ever bought this explanation. But the point is that if Elizabeth were alive today, she would point at the equation for the core theory and say, if you want to believe in something over and above the physical world, how does that change the behavior of the particles in your brain as it is predicted by that core theory equation? It's not enough to say, well, there's things we don't understand. If you don't think that the brain is simply the workings out of physical matter at some level, then you're saying that that equation is wrong. And saying how that equation is wrong is a daunting obstacle to overcome if you think that the world is more than just the physical stuff. And you don't need to think that. Even if you think the world is just physical stuff, it's perfectly okay to talk about things that we like to talk about when we discuss human beings, like choice and responsibility and morality. For exactly the same reason, it's okay to talk about temperature and density and pressure in a fluid, even though we know it's really made of atoms. These are emergent features of the world. If you're Laplace's demon, you can predict the future. That is true. There's no such thing as free will in the world of Laplace's demon. But we're not in that world. None of us has that ability. None of us knows the requisite information. Therefore, the best way we have to model the behavior of real human beings, real agents in the world, is as creatures who are able to make decisions. The problem only arises when you mix up the vocabularies. There are different vocabularies that can both be true, people making choices and atoms obeying the laws of physics, but you have to pick one or the other. If you walk up to your closet and say, am I going to wear the red shirt or the blue shirt? Oh, I'll just do whatever my atoms say the laws of physics are going to tell them to do. That does not make sense. You can talk about what your atoms do or what you're going to do. You can't talk about both at once. So this picture of the world that is just governed by the laws of physics isn't as bad as you might think in terms of recovering the human scale world of meaning and mattering and so forth. But there is a downside, namely that you're going to die. If you're made of the stuff of the core theory, if you're made out of the atoms and particles, then when you die, there's no place for the information that was in your brain to go. There's no known forces or particles that could carry that away if your atoms are actually still there in your brain. So one way of driving that home is to look at this plot that was made. There's some complexity theorists who like to study scaling laws in biology. It turns out that for mammals, there's a scaling law that relates your heartbeat to your mass, and also your life expectancy to your mass, and they cancel out. So everywhere along this curve, the total number of heartbeats in the lifespan of a mammal is about the same. It's about 1.5 billion heartbeats. Now humans are the exception because we invented medicine, Obamacare, and now we live for about twice as long as you would have predicted on the basis of this scaling relation. But then again, before we had modern medicine, we lived for 30 or 40 years, right on the line. So that means that we get about 3 billion heartbeats in our lives. There's no law of physics that says this. Biological progress can certainly extend our lifespan way, way longer than this, but we're not there yet. And if you believe that you are a bunch of particles that are interacting under that equation, this is the span of your life. You do not continue on after that. And 3 billion is a kind of a big number. 3 billion is pretty big, but it's not limitless by any stretch of the imagination. To me, claims like, well, if I'm just stuff obeying the laws of physics removes all the meaning and mattering from my life, don't hold water. Because to me, the fact that I only have this small period of time makes every little bit of that period much more precious. Every one of your heartbeats should be used to good effect. One way I like to drive this home, as the last slide, is the pale blue dot image of the Earth. So the Voyager spacecraft, one of the first spacecraft that left the solar system, when it was 4 billion miles away, Carl Sagan and his team convinced NASA to turn it around, take a parting shot, a photograph of the Earth and the rest of the planets in the solar system. So that little dot is us. That's the Earth, the pale blue dot. Every human being who has ever lived is in that picture, or at least their atoms are in that picture. So on the one hand, it makes you feel very small to think that all of us are just in that little bit, and this is not anywhere near the whole universe that we're looking at right now. But on the other hand, we did take the picture. That's pretty good. It's a selfie for the whole Earth. Voyager is just an elaborate selfie stick out there letting us take a picture of ourselves. But you know what? The ability to take a selfie shouldn't be underestimated. It is a reflection of the fact that even though we are very tiny compared to the universe, both in space and in time, we are in that complex phase. We are part of the universe that has gained the ability to think about ourselves, to be self-aware, to make choices for ourselves on the basis of rational reflection, to create technological marvels that can help us look at ourselves and think about what to do next rather than just moving from moment to moment. That's both the world we live in, which is true, and it's a world that we can try to work toward making the best we can which is good. Thank you very much.
So you connected the Big Bang to the arrow of time and the fact that the past seems different from the future. Can you also sort of use it to give an explanation for why it seems impossible to go back in time?
Well, yes and no. So this is a good question. The question is, there's an arrow of time that we attribute to the low entropy of the Big Bang. What about going backward in time? Mostly the fact that we can't go back in time is because that time is only one-dimensional. That's the real reason. We can go around in space, right? Because space is three-dimensional. If time were two-dimensional, there'd be no trouble to go back to the past. Basically, the fact that time is one-dimensional and the fact that, the world happens once at every moment in time means there's just no way to get there from here. It is actually not in any direct way related to what we call the arrow of time. Now that's complicated by the fact that in Einstein's theory of general relativity, space and time are flexible, and you can imagine building a wormhole or something like that that would get you to the past. And remember I said just a few slides ago that our impression that there is free will and choice is ultimately because entropy is increasing toward the future. So if you were able to hop in a wormhole like in Interstellar and go into the past, then your personal future would be the past of the universe. And which one wins? And that's a very good question to which no one has the right answer. Probably the simple answer is you can't do it. You can't go backward in time.
The emergent properties that come out of atoms or of us, do you think they're determined? When you said they're implicit, do they have to happen, or could there be other emergent properties from the same particles?
Well, this is a good question, too. Are the emergent properties determined in some way from the underlying stuff? Yes and no. I mean, ultimately the answer is yes, in the sense that if you believe everything I've said, then given that core theory equation, you could put it on a computer and uniquely find out what would happen in the future. So in that sense, everything is determined. There's the one very large footnote to that, which is, of course, quantum mechanics introduces some uncertainty into the game, as I personally am an advocate of the many worlds interpretation, where everything still is 100% deterministic, but not everyone agrees with me about that. So that doesn't give you any help whatsoever in the emergent properties business. It's still a rule. It's just a born rule for probabilities rather than some deterministic rule. So on the one hand, if you knew everything and had Laplacian demon-level intelligence about the underlying stuff, the future is determined, the emergent properties are determined, that's the whole story. On the other hand, you do gain new knowledge by figuring out what those emergent properties are. You have a way of talking about the system that is extremely algorithmically compressed compared to the microscopic way of talking about it. So even though the behavior is determined, you do learn something new by figuring out what the higher levels laws really are. And the higher level laws could be true even with different underlying stuff. The underlying stuff determines the higher level laws, but not vice versa. The way to become a successful biologist or psychologist is not to study particle physics. That's the fundamental rule here.
So you said that the core theory sort of explains and it will remain true for forever, basically. So at different moments in our history, we've had this sort of view of physics or mechanics or whatever. What makes this moment in human history different? That whatever we know will never change.
Well, again, it's not that whatever we know will never change. It's a very particular way of talking about the universe will remain accurate. Like Newtonian gravity was well established. Of course, now we know that the vocabulary used by Newtonian gravity is not the best vocabulary to use. Einstein's theory of general relativity came along and gave us a very good, better way of talking. And the whole vocabulary is different. Einstein talks about curved space-time and energy momentum. Newton talks about absolute space and time and forces and so forth. But it remains true that if you want to get a rocket from the Earth to the moon, you put Newton's equations into the computer. So there is a certain level of establishedness that a scientific theory has, past which it might be improved upon, but it will not be discarded. If you're thinking about things like the phlogiston model of combustion or the plum pudding model of the atom, those were never accepted as correct. The core theory is just as likely to remain true as the statement that this table is made of atoms is likely to be true. We might have a better understanding of what atoms are, but the table is not going to stop being made of atoms.
What are you working on these days?
What am I working on these days? I'm working on doing exactly this thing, which is making a better version of the underlying laws of physics. You know, we do have this problem that quantum mechanics and gravity do not play well together in extreme conditions, near the Big Bang, near the black holes, and so forth. So there are some of us who think that space and time themselves are not fundamental, that we need to do better at a quantum mechanical level of figuring out how space and time themselves are emergent from a deeper level of description. So I actually am ambivalent about time. Time may or may not be fundamental. I'm 99% convinced that space is not fundamental, and it's somehow a good approximation, just like the fluid description of the air in this room is a good approximation, even though it's ultimately made of atoms.
To a layperson, you say that the evolution of particles is pretty well described by the core theory, but the process of statistical mechanics seems a little bit more hand-wavy. It seems as though the way you enumerate states of the world and group them into categories really determines the predictions of your theories to a wild extent. Where do we stand in the evolution of statistical mechanics then?
Yeah, I mean, you put your point on a very important point. It's actually related to the earlier question. Statistical mechanics speaks a language of coarse graining and macroscopic states. So if you have a bunch of air in this room, like we have right now, and you know that it's made of air atoms and molecules, you want to describe it in a coarse-grained way as a fluid with a temperature and a pressure and a density. Well, that's one way of describing it. That's one sort of macroscopic description, but there are many ways. For example, when we really coarse-grain, we take a little region of space, like 1 cubic millimeter in size. We take the average number of particles and the average motion of those particles, and we relate them to macroscopic features of temperature and density and pressure and so forth. But who says that's what you can do? You could imagine taking a little tiny cube in momentum space rather than physical space. You could coarse grain that way. You could reduce your number of variables that way. What you would end up getting is a horrendous mess. And that's because, given the actual configuration of stuff in the world and the laws of physics, there's some reductions from many, many particles to much smaller macroscopic descriptions that work nicely and some that don't. So even though it in principle sounds very arbitrary, in practice, this gain in knowledge and understanding that you get from moving to the macro level is highly, highly constrained. We don't know all the details of how it should work in general. It's usually something where we know it when we see it, which is not nearly satisfying enough. We want to do better. But there does not seem to be multiple incompatible macroscopic descriptions of the same realistic underlying stuff. There might be in special circumstances, but in the real world that just doesn't seem to be a problem. So I think there's an interesting issue at the intersection of philosophy and physics here about why that is the case, but in practice that really does seem to be the case.
You spoke a little bit earlier about the Higgs field, and when you excite it, you get the Higgs boson, and then you also mentioned that there might even be a new particle on the horizon with it, you know, as we add more and more energy to the systems or our collisions. Do you foresee if that we'll just keep discovering, or there's an infinite number of particles? And actually, I have a even more fundamental question, which is, what is the meaning of these particles that exist almost for less than an instant?
Right. I mean, well, both these are good questions. I don't think there are an infinite number of varieties of particles. This is just my guess. What do I know? We don't know. This is the only correct and humble thing to say. But I think that given the existence of gravity, you can have particles that are infinitely heavy. They become black holes at some point. So there's probably some finiteness to a list of all the different kinds of particles we can imagine having. Sorry, what was the other question?
What's the point of those?
What's the point of them? They don't have a point. They're just there. Not everything needs to have a point. Things can just be.
How can you be so sure that those pointless particles don't have a point in our everyday existence?
Well, that's a good question. In the 6-hour version of this talk, or in the book that you can buy right now, I explain why. Basically, there's different ways that other particles could exist. They could be so heavy that you need a $10 billion particle accelerator to make them. They could be so short-lived that even if you bring them into existence, they disappear almost instantly. Or they could be so weakly interacting that even if they were there, they would go right through your body. All of these are ways that particles could have avoided detection, but in every case, they will not be interesting or useful in your everyday life. They would not have a point.
Would they have a point to any important feature or fact about the universe?
They might, yeah, they might play a role in sort of understanding how the different forces of nature unify at high energies or something like that. But again, you know, the idea that things have points is not part of the fundamental nature of reality, right? I mean, this level of meaning and purpose and causality is a higher level emergent thing. It's not something we have the right to demand from the fundamental architecture of reality.
You mentioned that you were somewhat certain that space was not a fundamental. What gave you that certainty, or what gave you that evidence?
So why do I think that space is more likely to be non-fundamental than time? For one thing, quantum mechanics intrinsically treats time and space very differently. The fundamental equation of quantum mechanics, Schrödinger's equation, has time in it, but it doesn't have space in general. So there's a chance that time really is fundamental just for that reason. The Schrödinger equation might not be right, it might not be the right description, so that's why we are still not certain, but there's at least a fighting chance. Whereas space is just obviously not fundamental. Space is something where when you go from classical mechanics to quantum mechanics, space more or less disappears. You know, in classical mechanics, what do you have? Some particles moving through space with some velocities. In quantum mechanics, you have a wave function of all those particles. And that wave function, we tend to talk a language that the wave function is a function of all the particles and their locations in space, but we don't have to talk that language. We can use what is called the momentum space description. We can completely describe the particles by how fast they're moving instead of where they are in the universe. And for that matter, we don't need to use any description at all. We can just use these quantum mechanical states in their own right, with no reference to space whatsoever. So the kind of thing I'm doing, you know, right now is trying to figure out ways to answer the question, someone hands you a wave function, a quantum mechanical state. Can you figure out what it is describing at the classical level? How many particles moving in what kind of dimensional space, et cetera. So everything we know about quantum mechanics, quantum gravity, et cetera, denigrates space into something that is just a good approximation at low energies. Thank you.